All right. So first of all, thanks to the organizers for inviting me. And I will talk about some work I've been doing together with Maxime Gabella, Chan Park, and Masahito Yamazaki. And our work is about BPS states in 4D unequal to quantum field theories. But in fact, it's also closely related to several topics in mathematics, including Hitchin systems, cluster algebras, and several others, because this is a topic in which there's been lots of very productive interaction between physics and mathematics. And in fact, over the past few years, there's been quite exciting progress. And one of the major achievements is that it is nowadays possible to compute BPS spectra systematically, thanks to the development of powerful frameworks such as BPS quivers and spectral networks. But one of the most interesting aspects of this field is that the BPS spectrum of a theory isn't unique. So a theory can have sometimes infinitely many different BPS spectra. And so just being able to compute the spectrum isn't quite answering all the questions about this topic. So a major step forward was the discovery of wall-crossing formulae, which describe how the spectrum changes across different regions of a moduli space. And an important idea which came out of this development is the existence of certain quantities known as wall-crossing invariants, which encode all the possible BPS spectra of a theory. However, in order to compute the wall-crossing invariant, one often needs to know in advance what the spectrum is. So this is what my talk will be about today. And the goal will be to introduce a new kind of wall-crossing invariant, which we call BPS graphs, and to explain how they establish a link between spectral networks and BPS quivers, and in what sense these are invariants. Namely, they provide a new construction of the invariant of Kontsevich and Soibelman, which moreover does not use any information about the BPS spectrum. So the setting will be that of theories of class S. These are 4D unequal to quantum field theories, classified by a Lie algebra, which will be of A type for today, a Riemann surface with punctures, and certain data. And a characteristic feature of theories of class S is that their low energy dynamics is described by the geometry of a Hitchin system. So the same data which defines the theory can also be used to formulate Hitchin's equations. And there's a Lagrangian fibration of the Hitchin system, whose base is identified with the Coulomb branch of the gauge theory, and therefore the metric on the base encodes the low energy effective action. But moreover, the metric on the full Hitchin moduli space turns out to encode information about the BPS spectrum of the theory. And so a peculiar feature of these theories is that one can study their BPS spectra by studying the geometry of Hitchin systems. So this has been a very fruitful idea, and a very convenient approach is to study the spectral curve, which is defined by the characteristic polynomial of the Higgs field. And sigma lives inside the cotangent bundle of C, and its sheets are, so it's a ramified covering of C, and the sheets are just the roots of the polynomial, which I'll denote by lambda j. And the way this encodes the low energy dynamics is by identification with the Seiberg-Witten curve of the theory, which means its homology lattice classifies the charges of BPS states. The periods of lambda are the central charges. And in this setup, BPS states arise as minimal area surfaces, which end on the spectral curve along cycles classifying their charge. And these surfaces stretch along fibers. They project down to one-dimensional paths on C. And so the mass of a BPS state, which is the area of the surface, can be written as the integral along this path of the separation of the two sheets. Now this is relevant because the BPS condition says that the mass equals the absolute value of Z. And given these characterizations, we have a new way of characterizing BPS states, which is really a reformulation of the BPS bound, which says that BPS states are trajectories on C along which the phase of lambda I minus lambda j is fixed and equal to the phase of the central charge. Now, this is not quite just a reformulation of the BPS bound. It's a very strong condition which is not satisfied by most homology classes. So only those which satisfy this condition are stable BPS states. And of course, which homology classes satisfy the condition is directly determined by the geometry of sigma. So there's a very direct relationship between the geometry of the spectral curve and the BPS spectrum. And this motivates the following construction. So to study BPS states, we fix a point in the base. That is, we fix the geometry of sigma. Then we look for the branch points of the cover, where lambda I equals lambda j. And we grow some trajectories out of the branch points, subject to the constraint that along the trajectory, the phase of lambda I minus lambda j is fixed and equal to some auxiliary phase theta. So we grow these trajectories, and then we look for those which end on some other branch point, because these are the finite trajectories, the ones that lift to closed cycles, to finite mass BPS states. So there are no such trajectories in this picture, but one has to look for all values of theta. As we vary the phase, we see that trajectories move around, and for some values of the phase, there is a finite edge like this. And these are BPS states. So what I just described is a sketch of the basic idea behind spectral networks as developed by Gautamura and Knightsky. And what's important for today is that BPS states arise as some finite edges which appear as topological jumps of the network, and these occur precisely at the phases of the central charges. Now, that's not quite the end of the story, because, as we said, BPS states can form bound states, and these can become stable or unstable whenever the phases of central charges are equal. So this happens at real codimension 1 walls of marginal stability within the Coulomb branch, and across a wall, a whole bunch of bound states, so gamma and gamma prime, can become stable or unstable, so the spectrum jumps. And we can think of this from the viewpoint of the geometry as due to the fact that the geometry of sigma changes a little bit, but just enough that there's a transition in the BPS spectrum. So some of those finite edges will just disappear. So to recap, we can use spectral networks to extract the BPS spectrum from geometric data of the spectral curve, but then this data is not invariant. It jumps across walls of marginal stability. So one can ask the question whether we can use spectral networks to extract some invariant information from the geometry of sigma. And in fact, the answer is yes, and that's what BPS graphs are about. So to define a BPS graph, we need to go to a special locus inside the Coulomb branch, which I'll call the critical locus. And this is defined as the place where the phases of all central charges of BPS particles are the same. Now, at the critical locus, if we tune the network to the phase of all BPS states, then this becomes very special, because at the phase of a BPS particle, there's a finite edge which appears within the network. But now all BPS states have the same phase, and so all these finite edges must appear simultaneously. So they form a graph within the network, and this is what we call the BPS graph. However, this is a funny place to look for information about BPS spectra, because, as you may have recognized, the critical locus is an intersection of walls of marginal stability. And this means that the BPS spectrum is actually ill-defined. So at first sight, it would appear that there cannot be any meaningful information here. But as I'm going to show to you, it turns out that BPS graphs encode invariant information about the spectrum. So let's start with the simplest example, which is the original Argyris-Douglas theory. The Coulomb branch is the complex plane, and the critical locus is the blue circle. So if we choose a generic point in the Coulomb branch, say u equals 0, and we study the spectral network, we see two jumps, which correspond to the two BPS particles which populate this region. Then if we move on to the critical locus, and we study again the spectral network, we see there's a single jump, where both of those edges now appear simultaneously. So that is the BPS graph of this theory. It's very simple, and that's actually an important property of BPS graphs. And nevertheless, it encodes some interesting information. So first of all, each edge can be lifted to a closed cycle on sigma, and their homology classes are, in fact, charges of stable hypermultiplets in any nearby chamber. We can also infer from this graph that these form a positive integral basis for the homology lattice, and we can compute their intersection. So in other words, what this graph encodes is something known as the BPS quiver of the theory, which is the Kronecker 1 quiver. Now, the story, of course, generalizes, and first of all, by a BPS quiver, I mean an oriented graph composed of a set of nodes and a set of arrows, and endowed with a superpotential function, which is a sum of cycles in the path algebra. And they encode BPS states as the zero modes of quantum mechanics encoded by the quiver. And given a BPS graph, there is a very general way of computing a quiver, and the first step is to realize that the BPS graph has a natural decomposition into elementary webs, which, roughly speaking, is obtained by removing the branch points. Then each elementary web is dual to a node of the quiver, and one can compute the arrows by counting the number of branch points shared by two edges. One can also compute a superpotential by summing over the loops of arrows that go around faces of the graphs and loops that go around the vertices. And then finally, there's an important operation on quivers, which is called quiver mutation, which has a counterpart at the level of the graph, which is just a flip of an edge. So that's the general correspondence. And in the case of A1 theories, this actually works very nicely. So in this case, the Coulomb branch parameterizes quadratic differentials. And the critical locus turns out to correspond to a parameter space for a particular kind of Strabel differentials. So BPS graphs in this case are a special type of Fenchel-Nielsen networks. And more importantly, their existence is actually guaranteed. There are theorems of Strabel and Liu which guarantee the existence of the critical locus and of BPS graphs. In fact, in A1 theories, BPS graphs are quite simple. They're just dual to ideal triangulations of C. So we don't even need to draw the spectral network. We can just choose an ideal triangulation, draw the dual graph. And then by our duality with quivers, we just recover a well-known story in the mathematics and physics literatures, which associates quivers to triangulated surfaces. So for A1 theories, we actually don't get anything new, but we get some rather extensive checks that our construction makes sense. Now, things are more interesting in high rank. Now, the Coulomb branch parameterizes meromorphic K differentials with prescribed poles. And in this case, we don't even know if the critical locus exists a priori. There's no high rank version of Strabel's theorem, as far as I'm aware. So what we can do in this case is to restrict our attention to K differentials with poles of order K, known as full punctures. And then in this case, we conjecture that there is a critical locus on the Coulomb branch. And we conjectured that the BPS graph is again dual to an ideal triangulation, where we take each triangle, we place n choose 2 branch points inside, and we connect them with some elementary webs in this way. So this is a conjecture, but it gives some candidate BPS graphs for all high rank theories with full punctures. It is motivated by a construction known as the lift of A1 theories of Gayatto-Morenaisky, which essentially is a systematic way of looking for this kind of loci. And of course, we found some explicit examples. So we found this loci, we checked that the BPS graph indeed looks like this, and that the dual quivers correspond to previously known BPS quivers for these theories. But we can do slightly better, and we can go beyond full punctures because, as it turns out, full punctures are the most general kind of punctures, in a sense. So one can obtain other types of punctures by just specializing the data, which is the residue of the Higgs field at the puncture. So for example, in a Hitchin system of A2 type, one can go from a full to a so-called simple puncture by taking the residue of phi and specializing M1 equal to M2 in this way. Then we see that the pole of the discriminant of the spectral curve jumps from degree 6 to degree 4. And what that means is that 2 zeros of the discriminant which correspond to the branch points of the spectral curve, must end up onto the puncture. But now, the branch points are also the vertices of the BPS graph. So what's happening here is that as we tune the moduli of the puncture, there's a topological transition of the spectral curve, which is reflected by the BPS graph, and this is shown in these pictures. And so we get a new BPS graph for the theory with the simple puncture, which looks like this. So this is just a very basic example, but it illustrates what's a general idea for obtaining other BPS graphs, starting from those for full punctures, and for obtaining several new quivers for higher rank theories with several types of punctures. So next, I would like to tell you a little bit about the other application of BPS graphs, which is to give a new construction of wall-crossing invariants. So the wall-crossing formula of Kontsevich-Soibelman describes how the BPS spectrum jumps across walls of marginal stability. And it does so in terms of products of quantum dilogarithms taken over all BPS states with charge gamma and spin m. And these products involve non-commutative quantum torus variables, x gamma. So the ordering is important. That's specified by the phases of the central charges. And which factors appear is determined by certain integers, which, roughly speaking, count the number of states with a given charge and spin. So the wall-crossing formula says that across a wall, some of the phases exchange their ordering. So there's a jump in the phase ordering, but there's also a jump in the spectrum, and these two are precisely such that they cancel each other. So the formula says that this product, which is taken over all BPS states, is actually invariant under wall crossing, and this is the definition of the wall crossing invariant of Kontsevich-Soibelman. So this is also known as BPS monodromy in physics. And this definition is great for studying BPS spectra. You can infer how the spectrum changes. But it's also slightly unsatisfactory in at least two ways. First of all, it's not very practical. There are some theories which only have infinite spectra. Then it's just hard to compute. But more fundamentally, it's not manifestly invariant under wall crossing. So wall crossing invariance is a highly non-trivial property of this object. So BPS graphs, as I'll show in a moment, give a completely new construction of this object, which improves on both of these points. And to explain how this works, I need to go slightly back to the definition of spectral networks. So in addition to the geometric data, there is also certain combinatorial data in a spectral network. And I will not tell you what this is or how it is computed, but what really matters for today is that it only depends on the topology of the network. So this data can be used to define a coordinate system on the Hitchin moduli space, viewed as the moduli space of flat connections on C. We heard about this in Lotte Holland's talk. And an important property of this coordinate system is what happens at the phases of BPS states. So when we hit the phase of a BPS state, the spectral network topology jumps, so the combinatorial data jumps, and the coordinate construction also jumps, and the change of coordinates takes this form. So they get conjugated by quantum dilogarithms, controlled by the BPS degeneracies of BPS states. Now, if we keep varying the phase of the spectral network across the phases of all BPS particles, then we collect all these changes of coordinates in an order which is dictated by the phase ordering of central charges. So by definition, if we compare the coordinates at theta and theta plus pi, we get an overall change of coordinates, which is precisely the BPS monodromy. And this observation is especially useful at the critical locus because now all BPS states have the same phase, so there is a single jump, and this jump is precisely given by the monodromy. But now we can turn this around, actually. We can take this as a definition of the monodromy. Namely, we can use spectral networks to compute coordinates before and after the jump, and then by using these expressions, we impose this relation, and this will characterize U. To actually carry out this program, there's a key fact, which is that the change of coordinates is entirely determined by the topology of the degenerate piece of the network, which is precisely the BPS graph. So the claim is that the topology of the BPS graph completely determines the BPS monodromy. And just to show you a few details of how this actually works in practice, let's again consider the simplest theory. So each of these two edges of the BPS graph contributes an equation of this type, where f and f prime are certain functions of the coordinates, which are computed from, by a simple combinatorial problem based on the topology of this graph. And then imposing these equations for each of these edges, one can compute the BPS monodromy. So it's actually easy to solve this system of equations. There's an algorithmic way of doing so. Slightly more involved is this example with three edges, P1, P2, P3. But again, the story is the same. Each edge gives an equation of this type. And again, f and f prime are computed by just combinatorics on this graph. And again, one can solve the equations and find the factorization. Now, before I wrap up, a couple of important remarks. So first of all, it is sometimes the case that BPS graphs have some symmetries. And these are important because by construction, they're automatically inherited by the BPS monodromy. Now, in this example, well, you may see that there's a Z3 symmetry permuting P1, P2, P3. This is manifest at the level of the equations, as you see, but it's completely hidden in this factorization into quantum Dell algorithms. So this is an interesting advantage of this construction, which is moreover important for making contact with the conjectural relation between BPS monodromies and specializations of the superconformal index. Now, my second remark is, how do we think of the monodromy physically at the critical locus? BPS states are ill-defined. The short answer is there's a lot of physics behind this. The key idea is to use surface defects to probe the theory. This induces the presence of a new type of BPS states, and the monodromy can be thought as describing the frame 2D 4D wall crossing of these BPS states. And what is really key here is that 2D 4D states are actually well defined even at the critical locus. So this is what physically justifies the computation of the monodromy. So to wrap up, we define new objects called BPS graphs on the UV curve of a theory of class S. These establish a link between spectral networks and BPS quivers. And they're also interesting because they give a completely new construction of wall crossing invariants of Kontsevich and Soibelman, which is manifest invariant under wall crossing in the sense that it doesn't use information about the spectrum. And it has the added advantage of exhibiting symmetries of the monodromy directly at the level of the graph. And with that, I'd like to thank you.